So let's talk about parametric equations and eliminating parameters. Now, why have parametric equations? Parametric equations basically allow us to show another variable, another parameter, if you will, and to introduce a parameter t. And so essentially what we have is t, where x depends on t and y depends on t, and I have a starting point and a stopping point. Now, because I have a square root function, t is going to be restricted. T is going to have to be greater than or equal than 1 and going to be a restricted domain. So we're going to start at t equals 1. If I plug 1 into my x function, I get 0. If I plug into my y function, I get 3. So my first point is going to be the point 0, 3. Now on the Cartesian plane, I can't see t as a factor. So typically what we do is we use arrows to indicate motion and time, or the parameter t. Let's plug in t equals 2. 2 minus 1 is 1, square root of 1 is 1. 2 plus 2 is 4, so my next point is going to be 1, 4. If I plug in 5, and I chose 5 strategically because if I plug in 3, I'm going to get roots that I really don't like. So let's just go with 5. 5 minus 1 is 4, square root of 4 is 2. 5 plus 2 is 7. So now I have 2, 1, 2, 3, 4, 5, 6, 7. And because there are no other further parameters, this thing is going to continue in this direction. You will typically see arrows to indicate movement. Okay? In pre-cal, you guys did something called eliminating the parameter. So let's discuss how to do that. Right now, I have two individual equations, one for x and one for y. I want to eliminate that and go back to a Cartesian xy equation. So if x is equal to the square root of t minus 1, squaring both sides will let me know that t is equal to x squared plus 1. I can then say, okay, well, if y is equal to t plus 2, let's take our expression for t and substitute it in so that we find out that y is equal to x squared plus 3. And that becomes pretty easy to see that this looks like half a parabola that has been moved up 3 units. However, the restrictions are that x must be greater than 0, since clearly the time restriction or the t restriction only gave us half of this parabola. Let's do one that's maybe a little bit more involved. So now I've given you one where t actually does have restriction. And t doesn't have to be time. I'm saying time, but it doesn't have to be. It's just another parameter. What I would typically recommend is set up a t, an x, and a y chart. And everything we're doing, this is pre-cal review at this point. So we're going to plug in -2, -1, 0, 1, 2, and 3 just for giggles. Plugging in -2, we should get 1 for x and -4 for y. Plugging in -1, we get -2 for x and -2 for y. Plugging in 0, we get -3 for x and 0 for y. -2 and 2, 1 and 4, and 6 and 6. Now important, direction and initial point is really important. So if I'm starting at 1, -4, 1, 2, 3, 4, that's my first point. Then I'm going to -2, -2, -3, 0, -2, +2, 1 and 4, and 6, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And I'm going to indicate direction of movement. And this is going to have endpoints on both points since the restriction of t is bounded on both sides. So we're not continue on with arrows. To eliminate the parameter, we'll do exactly what we just did before. You can start with x or y. In this case, I'm going to start with y since this looks like a function, like a parabola maybe turned on its side. So to eliminate the parameter, if y is equal to 2t, that means that t is equal to y over 2. taking my equation for x is equal to t squared minus 3, I can make a substitution. And determine that x is equal to y squared over 4 minus 3. And I opted to solve this for x since it looked like this was not a function. This was a function maybe defined, a function of x, or a function of y, excuse me. And it does look like this is going to be bounded for y between -4 and 6. Now, the most difficult of all three of these examples is the last one. So I gave you some trig. You can handle it. Let's plug in t and x and y. And because, let's just see what happens. Let's start with 0 and see what happens. If I plug in 0, cosine of 0 is 1, 2 times 1 is 2, 3 times 2, or 3 plus 2 is 5. If I plug in 0, sine of 0 is 0, which is going to give me -1. So we're going to start at 5, -1. 1, 2, 3, 4, 5, -1. If I go to pi halves, and I'm going to pick convenient values, we should get 3. And then for our y function, pi halves should give us 2. If I plug in, let's go ahead and graph that point. 1, 2, 3, 1, 2. If I plug in pi, we get 1 for x and -1 for y. And if I plug in 3 pi halves, we've got 1, -1. I should get 3 and -4. And interestingly enough, when I get to 2 pi, I'm back at 5, -1. So why is this happening? Well, what I have here is actually an ellipse. Let me prove it to you. Let's eliminate the perimeter. If I start with x equals 3 plus 2 cosine t, and honestly it doesn't matter what you start with this time, let's move x minus 3 is equal to 2 cosine t, which is going to give us that cosine t is x minus 3 over 2. Now this doesn't seem, don't solve for t, you're not going to get anywhere. But watch what happens. If I go y is equal to -1 plus 3 sine t, add 1, divide by 3, I can now say, hey, what do I know that can help me here? Well, we know that cosine squared and sine squared should equal 1. What happens if I make a substitution for cosine and say it is x minus 3 over 2 squared? And I make a substitution for sine, y plus 1 over 3 squared. Doing a little bit of math, I can say that this is now x minus 3 squared over 4 and y plus 1 squared over 9. And that is the equation of an ellipse that is centered at 3 and -1 and has a minor axis of 2 and a major axis of 3. So not too bad. Don't let that scare you though, because none of that was actually calculus. Let's do some calculus. So what do you have to know? Let's say we have a smooth curve C given by the equations f of t and y of t, or excuse me, f of t and g of t. And I want to find the slope of this curve, which we know to be called dy dx. Well, that means I'm going to have to take dy dt and divide it by dx dt. You're probably going to want to draw a line around that. Here's where things get spicy. If I ask you to find the second derivative, this is probably the number one mistake that students make. The second derivative is d2y dx squared, which is technically the derivative of dy dx. But that means I am taking the derivative with respect to t of dy dx, and I am going to divide by dx dt. Now, students very, very frequently mess this up. So why? Why is this the case? Well, if we consider that we are basically saying, take the derivative with respect to t of dy dx, and if I multiply by the reciprocal dt dx, watch what happens. This gives us d2y. My dt's go away, and I have dx squared, which takes us back to this formula. So what is this saying? Basically, I want to take the derivative of dy dx, and I'm going to divide it by dx dt again. So let's execute this with an example. If I have x is equal to t squared plus 9, and y is equal to 4t to the 5th minus 6t to the 3rd plus 3, I want to find the first and second derivative. The first derivative is easy. If I want to find the first derivative, I need to take the derivative of y with respect to t, and I need to take the derivative of x with respect to t. Well, the derivative of y is going to give me 20t to the 4th minus 18t squared. The derivative of x is going to give me 2t. I can simplify this by taking out a factor of 2 and t from the numerator to give me 10t to the 3rd minus 9t. In the denominator, 2t, for a final answer of 10t cubed minus 9t. But pay attention to this one. If I want to find the second derivative, I need to take the derivative of the first derivative, and I'm going to divide it by dx dt again. So what will I do? I'm going to take the derivative of this thing, d dt of 10t cubed minus 9t. So I'm going to take the derivative of that, and that will give me 30t squared minus 9. But you are dividing it by dx dt, which is 2t, again. I'm going to just write these up here for us, so we have those for reference. If you're going to miss one thing, you're going to forget that you need to divide by the dx dt again. It's a common mistake. So be very, very careful. That is your final answer for the second derivative. Now, you can do it again. Let's say now we have some trig. Here is x, here is y, and I'm going to add one more curveball to this. I want you to write an equation of a tangent line. So not only are we going to find a derivative, but we're going to find a tangent line. So we'll start by taking dx dt. The derivative of 5 sine of t is going to be 5 cosine of t, and dy dt is going to give us negative 3 sine of t. So that means that dy dx will be dy dt over dx dt. So negative 3 sine t over 5 cosine t. Well, conveniently, that's actually negative 3/5 tangent of t. Not required, but fun to write. We want to evaluate this at t equals 2 pi thirds. If we do that, we're going to get negative 3/5 times the tangent of 2 pi thirds. negative 3/5. Tangent of 2 pi thirds is going to give me negative root 3 for a final answer of 3 root 3 over 5. Not final answer, but that's your slope. Now here's where fun becomes. What do you need to write a tangent line? You need a slope and you need a point. I have a slope. I don't have a point. So that means we need to go up here and we need to find 5 sine of 2 pi thirds, which is going to give me 5 times root 3 over 2, or 5 root 3 over 2. And I also need to find 3 cosine of 2 pi thirds, which will be 3 times negative a half, or negative 3 halves. Now you have an x, a y, and a slope. Let's wrap it up with a tangent line. We're going to go y minus y1 is equal to slope x minus x1, and you're done. Now, another spicy curveball I could throw at you is I could say, hey, you know what? Let's find all of your points of horizontal and vertical tangency. So let's have a fast refresher on that. Remember that horizontal tangency is a slope of 0. Vertical tangency is a slope that is undefined. So we're going to put some things together. Start by finding your dx dt, which will give me 6t minus 6, and find your dy dt, which is 2t minus 8. That means when I go to find dy dx, I am dividing dy dt by dx dt, and I have 2t minus 8 over 6t minus 6. I would simplify this. Take out that 2 from the numerator and the 6 from the denominator, so that you have t minus 4 over 3 t minus 1. So I'm going to start with my horizontal tangents. Remember that horizontal tangents are where the slope is 0. That means I need to set my numerator equal to 0 because the denominator doesn't matter. So t minus 4 equals 0. That's going to happen at t equals 4. A vertical tangent is where the slope is undefined. So that means I need to set my denominator equal to 0. So 3t minus 1 is equal to 0. That's going to happen at t equals 1. But if you're not paying attention, you could easily mess this up. Guys, these aren't your answers. It says find all points. Those aren't points. I need to find the actual x and y values that go with these t values. So be careful here. If I go and plug in 4, what we end up finding is we're going to get an x value of 24 and a y value of negative 7. Don't trust me on that. Actually do it. So that means my answer is actually 24, negative 7. What am I plugging those into? I'm plugging those into the original equations. And if I plug in x of 1, we should get negative 3. And y of 1 should give me 2 for a point, negative 3, comma 2. So make sure you drive that one all the way home and read the questions very carefully. The final piece that we'll cover today is arc length. Now earlier we did learn an arc length formula for the length of a curve, but this was for function mode, for Cartesian functions. We learned that we're going to go from a to b of the square root of 1 plus the derivative squared dx. Now I use h because I had h in the function. Okay. Now remember that that is the same thing as the integral from a to b over the square root of 1 plus dy dx squared. dx. But there is a different format of this equation. What if I have parametric equations? Well, I may not be able to find dy dx, or maybe dy dx is going to end up being pretty spicy for me to find. So I want to show you how we could easily adapt this and come up with a new formula that works for parametrics. So if I have the integral from a to b, or x1 to x2, okay, of 1 plus dy dx squared dx, what I'd like to do is rewrite this as the integral from a to b of the square root of 1 plus, and let's use that new format. Let's say dy dt over dx dt. Let's keep it squared. All right, so from here, I'm going to find a common denominator. We're going to write this as dx dt over dx dt squared plus dy dt over dx dt all squared. And remember, I have that dx hanging out in the back. If I combine these all over 1 dx dt squared, then what I have is dx dt squared and dy dt squared dx. Keep in mind this is all under the house. I want to go ahead and take the square root of this and move it outside of the radical. So we can do that. Integral from a to b, radical dx dt squared dy dt squared. And remember, we moved it outside of the house. So there is just a dx dt in this denominator, and it's in the denominator because it was underneath the radical and a dx. We're in the home stretch. Integral from a to b, square root dx dt squared dy dt squared. Dividing by a fraction is the same thing as multiplying by the reciprocal. And then we still have our dx right here. Well, those dx's are gone. And what you've just discovered is your new arc length formula for parametric graphs. We're going to go integral from a to b. We're going to take the square root of dx dt squared and dy dt squared, and take it with respect to t. Now, I would prefer you not derive this every single time. I do think it is better to just go ahead and memorize it. So let's do one and call it a day. Here you have a function of x, function for y, and bounds. It says set it up, do not evaluate. Make sure you read those instructions. So we need to find dx dt. Derivative of e to the 5t plus 2 is going to be e to the 5t plus 2 times 5. Derivative of y with respect to t is going to be 3 cosine of t squared times 2t because of chain rule. Okay. When I go to set up my integral, we are going to integrate from 0 to 4 because these are bounds for t. We're going to take our 5e to the 5t plus 2. It gets squared. We're going to take I'm going to multiply that 3 and the 2 and go 6t cosine t squared. We're going to square it and throw dt, and you've now written an arc length equation.